So we continue now the lesson on hypothesis testing. Okay, so in the first few parts of our discussion last time, we introduced about the definition of hypothesis. And we also discussed the null hypothesis and the alternative hypothesis and some of their concepts. Okay, this time, we also discussed the two types of error. We have differentiated them, how type 1 error is different from type 2 error, and when do they occur. Okay, so this time we will now discuss the hypothesis tests for the mean. There are two common hypothesis tests when we test the equality of the means. We have here the z-test and the t-tests. Okay, z-test is applicable when your population standard deviation is known or the sigma is known. And t-test is appropriate when your sigma is unknown or what we call the population standard deviation. Okay, so this is the formula. We call it the test statistic, which is z or the z-test. This is equal to x bar minus mu divided by standard deviation divided by square root of n. N basically is the number of samples or the sample size. This is the sample mean, the x bar. The mu is your hypothesized mean, meaning this is the null hypothesis, the one that you have assumed. Since sigma is known, so basically we can solve the z-test calculated. Okay, for critical value for a two-tailed test for the mean, where sigma is known, we convert the sample statistics x bar to test statistic z using this formula. Okay, then we determine the critical z values for a specified level of significance alpha from a table. So this is what the table of the area of a normal curve. Okay, let me show you. So I already mentioned that there are lots of area of a normal curve or the z-table. This is just one where it covers the entire area of a normal curve. Okay, so you can notice that one if it covers the total area when you start your z of 0.00 with 0.5. Okay, so when you convert your sample statistics x bar to your standard normal curved, then your mu becomes 0 or the value of your mean becomes 0 if it is standardized normal. Okay, so this is what the z-table looks like, or the area under the normal curve distribution. Okay, you are already familiar with this. It was already introduced in the previous lesson. We go back to our lesson. Okay, then the decision rule would be, if the test statistic falls in the rejection region, we reject the null hypothesis. Otherwise, do not reject the null hypothesis. So I have already introduced to you how to determine the rejection area. So first, we have to determine the critical values. Okay, then if your value in this statistic, let's say for example, if your calculated C is within the rejection region, then you reject the null hypothesis. If it is within the non-rejection region, then you fail to reject, or basically do not reject the null hypothesis. Okay, so we go back to our first example. You are already familiar with this. If you could still recall, this 3 is equal to the number of TV sets. Okay, we use the problem number of TV sets in US homes. I hope you recall it. Your hypothesis is that you you assume your null hypothesis is that your population mean equals to 3. Okay, the mean number of TV sets in US homes equals to 3 against the alternative that it is not equal to 3. So it is a two-tailed test. If it is a two-tailed test, then we expect a rejection region both sides, the left and the right. Then your alpha is divided into 2. Okay, so this one is the lower critical value, and this is the upper critical value. If your Z calculated falls within the rejection region, then we reject the null. If it falls here in the non-rejection region, then we fail to reject the null. Okay? So it says here there are two cutoff values or the critical values defining the regions of rejection. Where do we find the critical values? It is in the Z table. Okay, so we have here steps in hypothesis testing. First, we state the null hypothesis or the H sub 0 and its alternative hypothesis, the H sub 1. Then we choose the level of significance or the alpha and the sample size n. So it is important that you have identified the sample size. Can we determine the appropriate test statistic, whether it is z-test or a t-test? Then we determine the critical values that divide the rejection and the non-rejection region. So if it is z-test, the critical values are found in the z-table. If it is a t-test, the critical values are found in the t-table or the t-tabulated. Okay, then the fifth step is to collect data and compute the value of the test statistic. Okay, compute the value of your Z if it is Z-test. Compute the value of your T if it is a T-test. Then the last is make the statistical decision and state the managerial conclusion. If the test statistic falls into the non-rejection region, do not reject your null hypothesis. If it falls into the rejection region, then reject the null hypothesis. And then you express your conclusion. Okay, of course, it is always in the context of the problem. So here, we complete our example. We test the claim that the true mean number of TV sets in US homes is equal to 3. Okay, then we assume its population standard deviation to be equal to 0.8. Okay, so first we state the appropriate null on the alternative hypothesis. So we have here H sub 0, mu equals to 3 against the alternative that mu is not equal to 3. Okay, so this is a two-tailed test because our alternative uses not equal. Okay, then we specify the desired level of significance and the sample size. Let's say, for example, your alpha, the alpha you set is 0.05. And say, for example, your n is 100. N again is the sample size. Okay? So, determine the appropriate technique. Since sigma is assumed, so it is z-test because it is already given in the problem. So, take note that we assume sigma to be 0.8. Okay? So, determine the critical values. For alpha equals to 0.05, the critical z values are plus minus 1.96. Why plus and minus? Because our test is a two-tailed test. So, there are values on the left of your z and on the right of your z. Take note that if it is a two-tailed test, we divide alpha into 2. So, that makes alpha over 2 to be equal to 0.05 divided by 2 or 0.025. Okay, where do we find this plus minus 1.96? Take note that our alternative is not equal to 3. So that is a two-tailed test. So if it is a two-tailed test, we basically divide alpha into 2. So 0.05 divided by 2, alpha over 2 is equal to 0.025. Take note that it is a two-tailed test. Okay, if it is a two-tailed test, okay, somewhat the normal distribution is like this. So we have here a critical value and a critical value on the right. So we write here critical value, then critical value. Okay. So this will be the rejection region. And here is the non-rejection region. So we're going to find this in the Z table. Take note that this one is 0. So we expect the value of our Z on the left is negative, and we expect our value of Z here to become positive. Okay? This one is 0.025. We're talking about the area, okay? And this is also 0.025. Okay? So we will find the critical values in the Z table. So since the area is given, we will focus on the values inside of our Z values. Okay? So if it is 0.025, then if we subtract 1 with 0.025, okay, so we will get 975. Okay, so left of Z value here is 0.975, and right of your Z here is 0.975 also. So we could start by looking the value of Z on the right of your 0. Okay, so that is 0.975. So where is that 0.975? This is 9719. So here, this is 0.9750. Look at this one. This is 1.9, and this is 0.06. So that gives us 1.96. So this is 1.96. Okay, this is also negative 1.96. Take note that a normal distribution is symmetric. Okay, so that's how you determine the critical values. Okay, we now move on to our fifth step. Okay, so given that your N is 100, and given that your sample mean is 2.84, take note that this sample mean is also given in the problem, and the standard deviation, the population standard deviation is also given, which is 0.8. Then if we calculate, we simply substitute the given values to the formula. X bar is 2.84. Your mu is your hypothesized value of the mean, which is a 3. Your sigma is 0.8, so that is 0.8. And your sample size is 100, so that's 100. Okay, you can use your calculator to calculate the value of your Z. Okay, so using your calculator, the calculated Z is -2. Okay, so remember that the value of your Z is -2.0. Okay, Okay, so we have determined the critical values, which is negative 1.96 and positive 1.96. The z calculated here is 2.0. So your z is negative 2.0, or you may also use positive. Although here the value of your z is negative 2, you could also use the positive value of your z by getting the absolute value of z. But if you will use the absolute value of z, you have to compare it with greater than. If you will be using the negative value of your z, you compare it with the negative value of your z alpha over 2. Okay? So if we are going to use the negative value of z, we will compare it with the negative 1.96. So negative 2 is less than negative 1.96, and that is true. Your z value falls within the rejection region. So therefore, we have to reject because it falls on the rejection region. Okay, so what if we are going to use the absolute value of z? So we take the positive value of z. So that is 2. Okay, so we reject if it is greater than 1.96. And that 2 is greater than 1.96, so it falls in the rejection region. So we still reject the null hypothesis. Okay, then we have to make our decision now. So since it falls within the rejection region, then we reject the null. Then we conclude that there is sufficient evidence that the mean number of TV sets in U isomes is not equal to 3. Okay, since we reject the null, we claim that it is not really equal to 3. It could be greater than 3. It could be less than 3. So we could conclude that the number of TV sets in U isomes could be greater than 3, or it could also be less than 3. Okay? We can also use the confidence intervals. Okay? How do we determine? Take note that this one is your confidence interval. Okay? If your value falls within the confidence, the non-rejection, then we fail to reject the null. Okay? So this is x, basically the confidence level. We will write it here. It's basically confidence interval. The CI is equal to, let us look at here. This is x bar. This is your z alpha over 2. And this is your sigma over square root of n. So that is x bar. Take note here. This is minus and this is plus. So we have here minus z alpha over 2 if it is two-tailed test, z alpha if it is one-tailed test, then sigma over square root of n. Okay, this is actually plus minus. So, or you could also write it here, comma. Here you use the subtraction and here you use the summation. You subtract here and then you add it here. So you use the minus here, the lower limit, and the upper limit is you use the plus sign. Okay, so we compare our hypothesized mean within. Okay, so our hypothesized mean is a 3. So since a 3 is not within the confidence level, it must be outside of your confidence level. So that only shows that Okay, so this our mu here is 3. Since a 3 is not within your confidence level, therefore it is not within the non-rejection area. So that is why we reject the null, because a 3 is not within your confidence level. That's how we use the confidence interval in determining whether we reject or we do not reject the null hypothesis. Okay? So what if the sigma is not known, or if it is unknown? Okay, if the population standard deviation is unknown, you instead use the sample standard deviation S. Okay, so most of the book, they uses the small letter for a sample standard deviation. Because of this change, you use the t distribution instead of the z distribution to test the null hypothesis about the mean. When using the t distribution, you must assume the population you are sampling from follows a normal distribution. You still assume that it is normally distributed. And then all other steps, concepts, and conclusions are the same. So the steps we use in the z-test is the same with the steps that we are going to use when we use t-test statistic. Okay? So the only difference is that, of course, it has a different formula. Look at this one. Our t-test statistic is equal to x bar minus mu divided by s over square root of n. So if you notice, instead of sigma, we use s because sigma is not known, but the sample standard deviation is known. Okay, let's say for example, the average cost of a hotel room in New York is said to be $168 per night. To determine if this is true, a random sample of 25 hotels is taken and resulted in an x bar, this is x bar, of $172.50 and a standard deviation of $15.40. So test the appropriate hypothesis at alpha equals 2.05. Take note the alpha is given and it is 0.05. Okay, so we have the hypothesis value of the mean, which is equal to 168, because we wanted to test whether the average cost of a hotel room is really 168 against the alternative that it is not equal. You could also use less than, because based on the samples, we get 172.50. So, I mean greater than rather instead of less than. So, we could also state our alternative to be mu greater than 168. Why greater than? Because in the samples, we get greater than 1.68. So, we could also use that one as alternative. But not equal is also correct. I mean, when you use not equal, that is also correct. Okay, so here, this is our hypothesis value of the mean. So since our alternative is not equal, we divide our alpha into 2 and we get this rejection region. Okay, so we will find out why is it that the critical values are plus minus 2.0639. Where did these numbers came? This is our C table. So first we have to determine the DF. DF, or the degrees of freedom, is n minus 1. So since our n is 25, we subtract it with 1. So we get 24. Okay? So how do you write your T tabulated or the T table? We simply write it in this way. T and then alpha and then DF. Okay? Since we have a two-tailed test, so this is alpha over 2. Okay, that is equal to T 0.025 because the given alpha is 0.05. and the DF is 24. Okay. Take note, the degrees of freedom for t-test is DF, or degrees of freedom, that is n minus 1. So since the sample size is 25 minus 1, so that makes it 24. Okay, look at here. Our alpha is 0.025 and our degrees of freedom is 24. So this is 24 and this is 0.025. So we get 2.0639. Okay, so that is why we have negative 2.0639 for the left side of your distribution, and for the right rejection region, the critical value is the positive 2.0639. Okay, so we calculate the t, or the t-test, using the formula. We simply substitute. Our sample mean is 172.5, and our mu, the hypothesis value of the mean, is 168. Then the given standard deviation is 15.40. Hope you recall this. Take note. This is the sample mean, is 1. And this is the standard deviation, the sample standard deviation. Okay, that is why we have here 172.5 and then 168 and then 15.4. So if you will calculate this one using your calculator, you will get 1.46. Okay, since it is two-tailed test, so we don't basically get its absolute value kasi it's because it is already positive. So we compare it with the positive value of your t. If this one is greater than your, if the t calculated is greater than the t table, then we reject. If it is less than, then we do not reject. Okay, so 1.46 is somewhere here. Basically, it falls within the non-rejection region, so we cannot reject the null hypothesis. Okay, and take note that 1.46 is less than 2.036. So that is why we do not reject the null hypothesis. We conclude that there is insufficient evidence that the true mean cost is different than 168. So okay. So in many cases, the alternative hypothesis focuses in a particular direction. So here we could also write our null hypothesis into greater than equal to 3, and then against the alternative that it must be less than. Okay, this is, and we reject the null hypothesis. We say that there is sufficient evidence that the hypothesis value of the mean is really less than. Okay, or the population mean is less than the hypothesis value of the mean. Okay, so if your null hypothesis is less than equal, alternative must be greater than. Okay, look at this one. So this is a lower tail test or a one-tail test, focusing on the left. Okay, so if the z calculated or the t calculated falls within this rejection region, then reject the null hypothesis. If it is an upper tail test, this is also a one-tail test focusing on the right. This will be your critical value. If your z or t calculated falls within this area, then you reject the null hypothesis. Okay. Example, a phone industry manager thinks that customer monthly cell phone bills have increased and now average over $52 per month. The company wishes to test this claim, so we assume a normal population. Okay, so our hypothesis, null hypothesis, is mu less than equal to 52, meaning the average is not over $52 per month, against the alternative that it is greater than 52, meaning the average is greater than $52 per month. Okay, so if we reject the null, then we conclude there is sufficient evidence. Okay, suppose alpha is 0.10, okay, and your n is 25. So since it is a one-tail test, our critical value is on the right because this is an upper tail test. Okay, so alpha is 0.10. The critical value is 1.318. Let's try to look at it in the t-table. Take note n is 25. So df is 25 minus 1. So that is 24. And your alpha is 0.10. Okay. So we look at the value of 0.10. This is 0.10. And we look at the df, which is 24. So this is 1.3178. Okay, so 1.318 or 1.3178 or 1.318. Okay, so we do not take the left rejection region because this is an upper tail test. Okay, so obtain sample and compute the test statistic. Suppose a sample is taken with the following results. N is 25, the sample mean is 53.1, and the sample standard deviation is 10. So calculate the t-tests. So substitute the given. Your mu is the hypothesized value of the mean. Look at this one. This is your hypothesized value of the mean, which is 52. Okay. Your standard deviation is 10, which is given. And then your n is 25. So using your calculator, you will get 0.55. Okay. So 0.55 is less than your critical value. So it falls within the non-rejection. So we fail to reject the null hypothesis. So we conclude that there is no sufficient evidence that the mean bill is over $52. Okay.